Okay, geometry, let's get rolling here on the last section of notes we have to take for the entire year here, and that is on 11.7. This is going to be really similar to a section that we did back in chapter 10, which was 10.4. And in 10.4, we started talking about perimeter and area of similar figures here. And remember that in chapter 10, we were dealing exclusively with two-dimensional figures. So the two formulas here that are going to kind of get harkened back to a little bit in this section right here is that when we had two figures that were similar, like for example, if we had a rectangle that looked like this, and then another rectangle that was similar to it but smaller, something like that, we had a proportional relationship right here between their perimeters. The perimeter of rectangle number 1 compared to the perimeter of rectangle 2 in the same manner as their corresponding side lengths. So this might be side 1 and this might be side 2 here. And then the second, more complicated version of that was that the area of figure number 1 was proportional here with the area of number 2 in the same ratio as the square of their side lengths here. Okay, so these were the two formulas that we needed in 10.4. The one thing that I want to point out, and it shows up a decent amount here in our homework, and we better get this one down too, anytime we take the ratio of two corresponding sides within two similar figures, the name for that, everybody, that you may have forgotten, is the scale factor. And it basically tells you how big one similar polygon is compared to the other. If I go back to this diagram right over here, and let's just make this nice and simple here. If I were to say that this side up here on the top of the first rectangle had a length of 8, and then the corresponding side over here on the second rectangle had a length of 6, we would say that the scale factor from figure 1 to figure 2 is 8 to 6, and of course we would simplify that to say 4 to 3. That becomes the scale factor now from figure 1 to figure 2. If we were ever reading it backwards from figure 2 to figure 1, that ratio would get reciprocated. It would initially be 6 to 8 and then would eventually become 3 to 4. Okay. So that's just a little bit of a recap of what we did in 10.4. Let's move on to the new things we have to cover right here in section 11.7. Now in chapter 11 we are dealing with three-dimensional solid figures, and the two measurements we've been making in this chapter of solid figures have been surface area and volume. And the important thing to remember before we move on right here is that surface area, just like this area formula that we did in 10.4, deals with area, which means it's a two-dimensional measurement. Remember that. Area is two-dimensional. So we would read this now to say that the surface area of figure 1 relates to the surface area of figure 2 in the same manner as their scale factor, side 1 over side 2, squared. Because again, surface area is a two-dimensional measurement, so we're going to square that scale factor, the ratio of their two corresponding sides, to get the ratio of their surface areas. So that's the first formula we needed here today. The second one deals with volume. And as we were just talking about how area is a two-dimensional measurement, we need to remember that volume is a three-dimensional measurement. So the ratio of the volumes of two corresponding figures, volume of solid 1 to volume of solid 2, is equal to now the cube of their scale factor, or the cube of the ratio of their corresponding sides. So V1 over V2 is equal to side 1 over side 2 quantity cubed. So if we can remember that surface area is two-dimensional, we put a 2 right there, but volume is a three-dimensional measurement, so that gets a cube right there. Now the good news is those are the only two formulas we need for this particular section of notes, and the rest of it's going to go pretty quickly. They're not easy problems, but those are the only two formulas that we need. So let's move on to problem number 2 right here. Okay, so we're talking about two solids and trying to get you guys used to what's coming right here. They don't always give you diagrams in these two figures right here, and so I left those out on purpose. Here's what we're saying here. Solid A has a side length of 5 inches, a surface area of 50 square inches, and a volume of 300 cubic inches. So that might not be a bad idea just to jot all that down. So solid A, let's write this out. So we'll call this side of A as a side length of 5 inches. The surface area of figure A, they told us here, was 50 square inches, and the volume of solid A was 300 cubic inches. All right, now we're going to talk about solid B, which is similar to solid A. None of this would work if these two solids were not similar to each other. Okay, in solid B, all we've been told is that the corresponding side length right here is 7 inches. And that's it. We're supposed to come up now with the surface area of figure B. Sorry, I should have put a B right there. Surface area of figure B and the volume of figure B. So that's what we've got to come up with here. Okay, so let's take a look at what's going on. These are two separate problems, everybody, so we're going to deal just with surface area first. And like everything else we've been doing for the last couple of months, we always need to start with formulas before we do anything else. And if we're going to try to find a missing surface area, we're going to go back to this formula right over here. That formula says that the surface area of figure 1, although I'm going to call that A in this case, compares to the surface area of figure B, in the same way as, here we go, the scale factor, side of figure A compared to side of figure B, but because we're talking about surface area, which is a two-dimensional measurement, that ratio needs to get squared. Now there are 4 unknown quantities within this formula right here. We better know 3 of them in order to be able to solve for the 4th. So let's fill in what we know in order. The first thing I see here in this blue formula is the surface area of figure A, which was given to us right here as 50. The next thing is the surface area of figure B. We don't know that, so we'll just go ahead and write surface area of B. It's basically a big ugly variable. Equals, don't forget the parentheses here, a side length in figure A was given to us as 5, and the corresponding side length in figure B was 7. So we'll put that there, and we'll square that. Okay. That's the setup, and it's a little bit messy, but this is the equation that we have to solve. Probably the first thing we would want to do here is deal with the exponent. And remember that when you're squaring a fraction, you square both the top and the bottom. So in a way, it's kind of like distributing an exponent. So I'm going to slide over here to the left, guys, because I think I'm going to need the room. 50 over the surface area of figure B is now going to equal, squaring the 5 gives us a 25, and squaring the 7 on the bottom is going to give us a 49. We have a proportion here, and we'd want to cross multiply that. Bottom left times top right, and top left times bottom right. So we're going to get 25 multiplied by the surface area of figure B, and that's going to equal 50 times 49. Let's see, 50 squared would be 2,500, so I think, oh hey, I have my calculator right here. How about that? So just to make sure, 50 times 49 is going to be 2450. And then we're going to divide both sides by 25 and get that the surface area of figure B equals, and I'm going to type in that 2450 divided by the 25, and it's going to get us 98. Units for surface area we were talking about before were square inches, so same units right here, and we get 98 square inches for the surface area of figure B. Okay. Half done with that problem. We still have to do all the work now to find volume, so I better start a new page right here. And let's start now with the formula for volume we talked about, which is this one right over here. All right, so volume of figure A divided by the volume of figure B is equal to your scale factor, side of A over side of B, but because volume is 3-dimensional, everything is getting cubed here. Okay, we know that the volume of figure A was 300 cubic inches. So we're going to put a 300 right up here. We do not know the volume of figure B. That's what we're looking for. Equals, and the scale factor here is going to be exactly the same as it was a moment ago when we did surface area. The corresponding side lengths are 5 and 7. So we close that in parentheses, and now we're going to cube that. Okay, so notice here it was 5 over 7 squared when we were talking about surface area. Now it's 5 over 7 cubed. Okay, same thing as before. We're going to apply that exponent of 3 to both the numerator and the denominator. So 300 over the volume of figure B is going to equal, that 5 cubed on top is going to get us a 125. The 7 cubed on bottom is 343. Everybody knows that one, right? Okay, now we're going to cross multiply. We're going to get a 125 multiplied by the volume of figure B equals, and that 343 we just came up with gets multiplied by 300 to give us a big old number here of 102,900. And the last thing we need to do then is to divide both sides by the 125, and we should be good to go here, so that the volume of figure B equals, okay, my 102,900 is still in my calculator. I divide that by 125, and I came up with an 823.2. Everything here was in inches, so since we're talking volume, that's going to be cubic inches for the volume of figure B. Okay, guys, so that is how that problem there works, looking at those two side by side right there. So, yeah, that's what we've came up with. The second figure, B, is definitely bigger than A here. 7 was bigger than 5. We came up with a surface area of 98, and our volume then was that 823.2. Now, just one thing I want to point out about these 6 numbers before we move on right here. If you look at the comparison of side lengths, 7 is obviously bigger than 5, but it's not bigger by a ton. It's not twice as big. In fact, 7 is just 40% bigger than 5. To get from 5 to 7, you'd really just multiply by 1.4. But if you look at surface area, from 50 to 98, the surface area almost doubles, and the volume almost triples. That really shouldn't surprise you guys right there. Surface area is a 2-dimensional measurement, volume is a 3, so those things do not all follow the same factor as you compare one to the next. Okay, the volume and the surface area tend to increase by a greater factor than just the side lengths did. Okay, let's move on to one more, and then I think we're done here, guys. Now we're talking about solids C and D. Pretty similar problem here, guys. So talking about solid C, let's see what's going on right here. Solid C has a volume of 80, and I think that's all we know about solid C. So the volume of C is equal to 80 cubic centimeters. Okay, and it says now that solid D has a volume here of 63 cubic centimeters. Okay, so now we're dealing with two figures here, and it looks like C is the larger of the two figures. Let's keep reading now. If a side length in solid D is 9 centimeters, so a side length in D is equal to 9 centimeters. We're supposed to find the length of the corresponding side in solid C. So we're looking for a side length here in solid C. That's the unknown within this problem. Okay, so actually this is a little bit simpler than the second one in that we don't have to worry about surface area at all, but we have our setup right here. So we're talking volume, so I'm going to open a new page right here to give us plenty of room here, and let's get working now on that second formula we wrote down earlier today, that the volume of one solid, I'm going to say the volume of solid C, compares to the volume of a similar solid, D, in the same manner as their scale factor, side of C compared to side of D, but since volume is 3-dimensional, that ratio, that scale factor, is going to get cubed. And let's fill in what we know. The volume of C was 80. We'll put that right here. And the volume of D, similar to it, was 63. Now over here, we do not know the side length in figure C, but the side length in figure D was 9. So I'm going to leave this right here as, I'll leave it as it was, S of C. If you want to put an X right there, which I would think a lot of you guys would want to do, that's perfectly fine. 9 centimeters was the length of the corresponding side in figure D. Okay, so this is the equation that we have right now, and I wanted to talk about how to solve this here. What I would think a lot of you guys would want to do is revert to what we did in the previous problem, where you took this exponent of 3 and applied it to both the bottom and the top. You can do that here, but I need everybody to understand that there's something different going on here in this problem compared to the one that we did previously. In the previous problem, the variable we were trying to solve for was not part of the exponent. The exponent applied to this fractional constant of 5/7. So we wanted to fully simplify this right side before we cross multiplied, and that's why I applied that exponent to the top and the bottom. Here we're going to do something different, and one thing I've tried to get you guys to change your thinking on this year is not just what can I do, but why would I do it when solving an equation. Our goal here is to isolate our variable, which is this S of C right over here. Now, if I ask you guys, what is being done to that variable? There's two answers. The first thing being done to S of C is that it's getting divided by 9. And the second and final thing that's happening is that they're cubing that. Those are the two things that we need to undo. And we need to undo the thing that is being done last first. The last thing being done here is a cube. So what we're going to do, and I honestly can't remember, guys, how much of this we've done so far this year. If we want to undo a square, we use a square root. But in this case, if we want to undo a cube, we do what's called a cube root, which looks like a square root. It's really a radical, but we put a little 3 right there, which is called the index of that radical, kind of nestled in that little spot right there. You guys may have seen this in the past. You're going to see a lot of it next year in Algebra 2. And of course, whatever we do to the right side, we do to the left side. Now on the right, a cube and a cube root cancel each other out completely. So the right side is now just going to be side length from figure C divided by 9. The cube and the cube root took care of each other. But over here on the left side, we've got to do the cube root of 80 over 63. And I'm going to try to show you guys how to do that on a calculator. And I wish that I had the calculator that you guys are using to be able to show you that for real. I don't, unfortunately. So let me see right here. If we were doing something like, actually, there's a cube root right there on the Desmos Scientific calculator. This might be one worth downloading if you guys needed to do that. And this button right over here, everybody, towards this lower left-hand corner, is the nth root of a button right there. So when I hit that right there, guys, you'll see my cursor is in the index. So I was looking for the cube root. Okay, and now I'm going to hit my right arrow, and the number I was trying to find the cube root of was a fraction. It was 80 over 63. So I'm going to go ahead and type all that in. You may need parentheses here in some cases, but this seems to be working out okay. That's giving me what I was looking for. The cube root of 80 over 63. Boy, unfortunately, this converted that right into a decimal, and I was really hoping it would try to simplify that radical for me, but we'll Let's see if I can do one other thing here. This TI Inspire CAS calculator that I'm using works a little bit more in some of these cases like your calculators. So if I was going to do that, I would hit a 3 first and then this button right here. Nope, I lied. That is not what I would do. Let's try that again. I'd hit this button first. I'd put a 3 there. And then for my radicand, I'd go ahead and I'd type in 80 over 63. And I believe this calculator is going to give me, oh dear God, the fractional version of that. Okay. So what have I learned here, everybody? This problem is a mess, and probably going with the decimal version was better than that mess that we had up there before. So I'm going to go with 1.08 for what to write down now for that left side here. So 1.08 is going to go right there. Now, asking yourself the question, where is my variable? What is being done to it? And how do I undo it? We see that there's an SC right here. That's our only variable. It's being divided by 9. So to undo that, we're simply going to multiply by 9. So S of C, the corresponding side length in C, is going to equal, and I want to take that last number right there. So on this calculator, I have to hit the answer button. You guys could just hit times. And now I need to hit times 9. And that should give us our answer here of 9.75 if we were going to round that to the nearest hundredth for SC, 9.75. We're talking about a side length here. Our volumes were all measured in cubic centimeters, but side lengths are measured in just plain centimeters. So that is the length of the corresponding side here in figure C. Okay, guys, that's a wrap on 11.7. Let's give that worksheet a try and see how we do on that. Post any questions you have in comments, and I'll be happy to work those out for you. Good luck.